Angle basics. An angle alpha is formed by two rays with a common vertex. Associated with an angle is its measure, generated by a rotation from one side of the angle, the initial side, to the other side called the terminal side. Here we have our visual representation of our angle alpha. Here's my vertex, the initial side, the terminal side, and this arrow indicates the direction of rotation. We often use Greek letters to denote angles. Some of the common ones are alpha, beta, theta, and gamma. Angle measures. Counterclockwise rotation gives a positive measure, and clockwise rotation gives a negative measure. Here are our visual examples. In this positive angle, we can see that to go from the initial side to the terminal side, we are going in a counterclockwise direction. Here's a negative angle where the initial side is up here and we go in a clockwise direction to get to the terminal side. The units for measuring angles are degrees or radians. Here's a brief overview of degrees and radians. For degrees, we say one complete revolution measures 360 degrees, and here's the notation. So one complete revolution is 360 degrees. So 1 degree is 1/360th of a revolution. For radians, we say one complete revolution is equal to 2 pi radians. So here we have one complete revolution around a circle is 2 pi radians. So one revolution is 2 pi radians, therefore 360 degrees is equal to 2 pi radians. These are alternate ways to measure an angle, and we can convert between the two. Here's some more angle vocabulary. An acute angle is an angle with measure between 0 degrees and 90 degrees. A right angle is an angle with measure exactly 90 degrees. An obtuse angle is an angle with measure between 90 degrees and 180 degrees. And a straight angle is an angle with measure exactly 180 degrees. And below are some visual examples of the types of angles. I want to pay a quick attention to a right angle. We see that a right angle has a little square in the bottom corner to indicate that it is a right angle, and that must be there. We can't just assume we have a right angle. When we look at it, if it looks like one, we have to see the little square. And we also have some terms complementary and supplementary. If the sum of two positive angles is 90 degrees, the angles are called complementary. And if the sum of two positive angles is 180 degrees, the angles are called supplementary. In trigonometry, we deal with a lot of angles in standard position. So an angle theta is in standard position if its vertex is at the origin of the xy plane with the initial side on the positive x-axis. So let's go ahead and take a look. Here we have an xy plane, and the vertex is at the origin 0, 0, and the initial side of the angle is along the positive x-axis. And here we have an example of a positive angle, since I'm going in a counterclockwise direction to reach the terminal side. But I can also go in a clockwise direction and have a negative angle in standard position. Now, when an angle is in standard position, it's either going to fall in a quadrant or on the x or y axis. So here we have the quadrants labeled 1, 2, 3, 4. They go in a counterclockwise direction. So I can either have the terminal side fall in a quadrant or on an axis. Now, an angle whose terminal side is on the x or y axis is called quadrantal. So thus the quadrantal angles are 0 degrees, 90 degrees, 180 degrees, 270 degrees. So I'm adding 90 degrees over and over again to get to the x or y axis. In radians, that would be 0, pi over 2, pi, 3 pi over 2, 2 pi, going around to those different x or y axis locations. Let's define coterminal angles. Coterminal angles are angles with measures that differ by a multiple of 360 degrees, or 2 pi. In other words, keep adding or subtracting 360 degrees, or 2 pi, to a given angle to find its coterminal angles. Given the angle alpha, all angles coterminal to alpha can be written as alpha plus or minus 360 degrees times n, or in radians, alpha plus or minus 2 pi times n, where n is an integer and alpha is the least positive coterminal angle. So this expression is just saying that we're either going to add or subtract n copies of 360 degrees. So we can continue to add 1 copy, 2 copies, 3 copies, or subtract 1 copy of 360, 2, 3 copies of 360. So n is an integer, as in 1, 2, 3, 4, 5, or 0, or -1, -2, -3. Those are the integers. So those are the copies of 360 that's going round and round and round. And in radians, we're just replacing 360 degrees with its equivalent 2 pi. We've so far reviewed a lot of definitions. Let's go ahead and look at an example now. So here we're asked to find one positive and one negative coterminal angle for each angle given. Then write the expression to find all angles coterminal to the given angle. Finally, sketch the given angle. So here we have -400 degrees. So we want to find one positive and one negative coterminal angle first. Well, to find coterminal angles, we either add or subtract copies of 360. So if I'm interested in finding one positive coterminal angle, and I start at -400 degrees, I'm going to have to add at least one copy, if not more, of 360 degrees. So here we'll go ahead and start with -400 degrees. If I add one copy of 360, I'm going to end up with -40 degrees. So I've actually now found one negative coterminal angle to -400. I have -40. So that itself is one of my answers. But I'm going to have to do it again. I'm going to have to add 360 to -40. And that will finally give me a positive angle. That's going to give me 320 degrees. So I found one negative and one positive coterminal angle. Then I want to write the expression to find all the angles coterminal to the given angle. So we only found one of each. If we want to write the expression to find all of them, what we're going to do is we want the least positive coterminal angle. So here, we've actually already found that 320 degrees is going to be the least positive coterminal angle to -400. If I add another 360, that's obviously going to be bigger. So we want the least positive. So we're going to put 320 degrees and then plus or minus 360 degrees times n. And then we want to say where n is an integer. So this is the expression that finds all angles coterminal to the given angle. And finally, we want to sketch the given angle. So the given angle up here in the problem was -400 degrees. So I'm going to go ahead and sketch my angle in standard position. So we're going to have our vertex at the origin, our initial side along the positive x-axis. Because we have a negative angle, we are going to go in a clockwise direction, and we have to go around 400 degrees. Well, one complete revolution is 360 degrees. So if I go ahead and start my motion here, I'm going to go in a clockwise direction, and I've gone 360 degrees so far. and then I need to go an additional 40 degrees. So if I go an additional 40 degrees, I end up about right here in quadrant 4. So here is my terminal side. So this right here is negative 400 degrees. So I went in a clockwise direction, negative 360, and then additional 40 to get me to negative 400. And when we find these coterminal angles, they will, when sketching these, they will take me to the same terminal side. So in other words, negative 40 degrees here would start along the positive x-axis and go in a clockwise direction because it's negative, and it's going to take me down here, and it's going to end along the same terminal side. If I think about 320 degrees, that's now going from the positive x-axis, the initial side, in a counterclockwise direction, 320 degrees. So down here, remember, is 270. So it's going an additional 50 degrees over here. So that's what we mean by finding those coterminal angles. Essentially, it's just different ways to arrive at the same terminal side. And this expression would give us all the possibilities, because I can just keep adding and subtracting copies of 360 and still end up at the same terminal side. Now we're going to take a look at an example that is in radians. So here we have the angle 5 pi over 6. That's a positive angle. So we're going in a counterclockwise direction. And let's go ahead and do a little bit of labeling. So here I have 0 radians, pi over 2. Here we have pi. So just as a reminder, right, this is 1 pi, or another way to think about it is it's 6 over 6 pi. And pi over 2, well, that's 3 pi over 6. So 5 pi over 6 is going to be between 3 pi over 6 and 6 pi over 6. So here, I'm going to think about kind of splitting this up into those 3 equal parts. So if I start along the positive x-axis, and I'm going to finish right about here. This is 5 pi over 6 with my terminal side. So I went ahead and sketched the given angle first, just because some students tend to struggle a little bit more with radians than they do with degrees. So here's my sketch. And now let's talk about finding positive and negative coterminal angles. So we're going to add and or subtract 2 pi. So we're going to go ahead and start with 5 pi over 6. And let's start with adding 2 pi. Well, here I have a fraction, 5 pi over 6. So in order to add 2 pi, I'm going to need common denominators. Well, that common denominator is going to need to be 6 over here, and that's partly why I started to sketch it first, so we can start to think about rewriting numbers with common denominators. So the common denominator, 6, I have to multiply the top and bottom by 6 here. So we're going to have 5 pi over 6 plus, if I multiply the top and bottom by 6, I'm going to get 12 pi over 6. So if I add the numerators, now that I have a common denominator, I have 17 pi over 6. So that is a positive coterminal angle. And to find a negative coterminal angle, well, I'll start with 5 pi over 6 and subtract 2 pi. But we already know 2 pi can be rewritten as 12 pi over 6, so I'm kind of just showing an extra step here. So we have 5 pi over 6 minus 12 pi over 6. Subtracting across the numerator, 5 pi minus 12 pi is negative 7 pi over 6. So here's a positive, here's a negative coterminal angle. And if we want to write all coterminal angles, that expression, we're going to make sure to use the least positive coterminal angle. Well, in this case, that's the original. 5 pi over 6 is the least positive. If I add 2 pi, that got me 17 pi over 6, that's bigger. When I subtracted 2 pi, that gave me a negative angle, which is not positive. So 5 pi over 6 is what we're starting with, plus or minus 2 pi times n, where n is an integer. Now you can write this expression, n is an integer, you can write it all out, but for anyone who's interested, we have some shorthand in math where we can say n is in the set of integers, which is this fancy, bold looking z. So this says 5 pi over 6 plus or minus 2 pi n, where n is an integer. N is in the set of all integers. So we can go ahead and keep this as our expression. Now let's define a reference angle. A reference angle, theta prime, to the angle theta is the positive acute angle made with the terminal side of theta and the x-axis. So in my visual representation here, what I have all on one xy plane is I have 4 different angles. And so I'm assuming that each of these colored lines here represents the terminal side of an angle. So here, we'll start with this first one. In quadrant 1, this black line here indicates the terminal side of an angle. And so the reference angle, theta prime, is actually just equal to the original angle. So a reference angle is the positive acute angle made with the terminal side and the x-axis. So here, the original angle theta is equal to the reference angle theta prime. But when I have an angle like over here in quadrant 2, so this green line here represents the terminal side of an angle in standard position. So we're assuming it started on the positive x-axis, it's ending over here in quadrant 2. So the original angle would be this one here. This would be theta. That would be the original angle. The reference angle is now this little angle here, which goes from the terminal side to the x-axis. So it has to be acute. Remember, acute means between 0 and 90. So it can't be this original theta that's obtuse, that's greater than 90 degrees and between 180. So it's got to be this angle here. This is theta prime. Now if we focus on the angle that's in quadrant 3, so starting along this positive x-axis, it's going to end over here in quadrant 3. That's theta, that's the original angle. Well, theta prime, its reference angle by definition, is this little angle here where I'm going from the terminal side to the x-axis in the shortest way possible, right? Like what's the quickest way to get there? Because I want that angle to be the shortest, I want it to be acute, right? I want it to be between 0 and 90. So I don't want to go the other direction. That's going to give me too big of an angle. So this is my theta prime for an angle that's in quadrant 3, where the terminal side's in quadrant 3. And then if I go all the way around to an angle in quadrant 4, so this would be like the original angle, that would be theta. Its reference angle, theta prime, is right here. So it's going from the terminal side, this red line, to the x-axis. Like the quickest, the shortest way to get there to form that acute angle would be this angle here, theta prime. So that's understanding this concept of a reference angle depending on where your original angle terminal side lies. Now let's look at an example. Sketch each angle theta and then find the reference angle theta prime. So here in part A, we're assuming 240 degrees is our theta, is our original angle. So let's go ahead and sketch 240 degrees. Well, we know this is 180 degrees, and this is 270 degrees, so 180 is directly left, 270 is directly down. So 240 degrees is going to be here in quadrant 3. So starts on the positive x-axis, goes all the way around, and basically how far past 180 degrees does it go? Well, it's going to go 60 degrees past 180. And in actually thinking about that, we've figured out what our reference angle is. So here's my angle, 240 degrees. So I'm indicating the direction here. It's positive, counterclockwise direction. And the reference angle is the acute angle between the terminal side and the x-axis. So let me go ahead and indicate that here. That's going to be this angle here, and that's going to be 60 degrees, right? So it's like how far away am I from the x-axis? The shortest direction, right? The quickest way. So my theta prime here is 60 degrees. Let's go ahead and try it with an angle that's given in radians now. So my angle is 7 pi over 4. 7 pi over 4. So I'm going to go ahead and start by labeling my quadrantal angles here. So 0 pi over 2, pi, 3 pi over 2. And I'll even go over here. 0 is also 2 pi, right? 0 and 2 pi are coterminal. And I want to think about denominators of 4 here, right? 7 pi over 4. So I can go ahead and think about this as this is 2 pi over 4, pi is 4 pi over 4. This is going to be 6 pi over 4, and 2 pi is 8 pi over 4. So here, where's 7 pi over 4 going to be? Well, it's going to be between 6 pi over 4 and 8 pi over 4. So I'm going to go ahead and sketch my angle. It's a positive angle as well. It's going to go counterclockwise, and it's going to land me right in between quadrant 4 here. So this is where my terminal side is going to end up. So this angle here is my 7 pi over 4 angle. And to find the reference angle, I want to know what's the quickest or the shortest way, kind of informally, to get to the x-axis, right? So it's going to be this angle here, and I want to know what is the measure of this angle. So if this is 8 pi over 4 and this is 7 pi over 4, the difference between the two is 1 pi over 4. So we're essentially just subtracting, right? 8 pi over 4 minus 7 pi over 4 makes my theta prime pi over 4. That is my reference angle.